Hello everyone. In this session, we are going to discuss about MOS transistor theory. Before that, a modern processor, right, contains billions of MOS transistors. To design fast, low-power VLSI circuits, we must understand MOS transistor theory at a device level. So here we are going to learn about MOS operation from VLSI and scaling and non-ideal effects here. So, what is the role of MOS transistor in VLSI? So, the MOS transistor, MOS, right? It is a basic building block of digital logic, memory cells, and analog blocks. Why we are preferring BJT over MOS here is its low power, high integration, and the scalability. So here, the MOS transistor, right? It behaves as switches and controlled current sources. In designer perspective, first we'll go with device requirements. This device, it's a combination. It has more advantage when compared to BJT. We are going for the MOS, and it's used in large scale integrations. And it's a low power circuit. We can easily use it. It's easily used in VLSI circuits. And since it's efficient, scalable, we are preferring MOS here. And now we'll go with the structure. Okay. First, we have gate that is which is exposed that is which of poly or metal, ultra thin oxide, source or drain, channel, and body terminal. These are the terminals. Normally, we'll have three terminals in mass: gate, source, and drain. Okay. Normally, we have substrate that will not be exposed explicitly, but the substrate will also be connected there. Next comes channel formation and threshold voltage. So normally we have in MOS, we have NMOS and PMOS. In IC fabrication and all, we'll always using CMOS. CMOS is a combination of PMOS and NMOS. CMOS is complementary metal oxide semiconductor. So it's a combination of NMOS and PMOS here. And so NMOS, right? It has accumulation, in depletion, and inversion and all. In threshold voltage, right, the threshold voltage depends on oxide thickness, doping concentration, and body bias. So this threshold voltage control, right, it's a trade-off between speed and power. Okay, this is the physical structure, how it looks. So we have gate, as explained previously. We have gate, we have drain, and we have source as well. So and we have a substrate here. And region of operation. Okay, so the MOSFET operating region, right? The cutoff region, when it will be acting as a cutoff region is when the gate source voltage is less than the threshold voltage, we'll be having a cutoff. It will be acting as a cutoff. Cutoff is nothing but it will be acting in off mode. Okay. Next in linear or triode mode. So in this, that is when your gate source voltage is greater than threshold voltage, and the your drain source voltage is lesser than the difference between the uh, gate source and threshold, will be acting in triode or linear or an active region. Next one is saturation. When your MOS will be acting in saturation region here is when your drain source voltage is greater than or equal to a gate source, and the difference between gate source and threshold. Okay, so that it will be acting in saturation region. In that also we have enhancement mode and depletion mode. Okay, your next one, there are some effects. Okay, short channel effects we'll be calling that. That is because of channel length modulation, velocity saturation, and rain induced barrier lowering. So, and we have, since we have NMOS and PMOS combined in CMOS, there will be some difference, right? So, for example, electron mobility and whole mobility, there will be difference. And PMOS, right? It's wider than NMOS, and these are the some differences. And this is the CMOS performance cycle here. You can just after getting the product, you can just make an evaluation, evaluate performance, identify areas for improvement, implement enhancements. So these are how it can be done. So this is the question. So initially VDS increases drain current. So but at a point the current saturates. So here's the question. Why does current does not increase forever like a resistors? So that's all with this session. We'll see you next class.